What happens when spacetime itself is disturbed? Einstein's general relativity tells us that gravity is not just a force pulling objects together. Gravity is connected to the shape of spacetime. When very massive objects move violently, they can send ripples through spacetime. These ripples are called gravitational waves. Gravitational waves are ripples in spacetime itself. In this video, we will see what gravitational waves are, how they are created, how scientists detect them, and why they opened a new window on the universe. Here is what this video will explain. First, we will review Einstein's picture of gravity. Then, we will see what gravitational waves are. Next, we will explain how massive objects can create ripples in spacetime. We will look at black hole mergers and neutron star collisions. We will also see why gravitational waves are so difficult to detect. Finally, we will explain how LIGO detects tiny stretching and squeezing of space. The main idea is simple: spacetime can carry waves. In Newton's picture, gravity is a force between masses. The Earth pulls on the Moon. The Sun pulls on the planets. This picture works very well in many everyday situations. But Einstein's general relativity gives a deeper explanation. Mass and energy curve spacetime. Objects then move by following paths through that curved spacetime. So gravity is not only about objects pulling each other. It is also about the geometry of space and time. In Einstein's view, gravity is curved spacetime. Gravitational waves are disturbances that travel through spacetime. They are often described as ripples in spacetime. The idea is similar to ripples spreading across water after a stone is dropped. But gravitational waves are not ripples in water. They are ripples in the geometry of space and time itself. As a gravitational wave passes, it can very slightly stretch space in one direction and squeeze it in another. The effect is incredibly tiny by the time it reaches Earth. A gravitational wave is spacetime carrying energy across the universe. Gravitational waves are created when massive objects accelerate in powerful ways. A single object sitting still does not create strong gravitational waves. Even ordinary motion usually produces waves far too weak to detect. The strongest gravitational waves come from extreme cosmic events. For example, two black holes orbiting each other can disturb spacetime as they spiral inward. Two neutron stars can also create strong ripples as they move around each other and collide. The faster and more massive the system, the stronger the waves can be. Violent motion of massive objects can shake spacetime itself. Some of the most important sources of gravitational waves are black hole mergers. Imagine two black holes orbiting each other. As they orbit, they lose energy by sending gravitational waves into space. This makes them spiral closer together. Eventually, they merge into one larger black hole. That final merger sends out a strong burst of gravitational waves. Neutron star collisions can also produce gravitational waves. These events may also produce light, gamma rays, and heavy elements. Gravitational waves let us listen to the collisions of massive objects. Gravitational waves are extremely difficult to detect. By the time they reach Earth, their effect is unbelievably small. They do not shake objects in a dramatic way like an earthquake. Instead, they change distances by less than the width of an atomic nucleus over kilometers of detector length. That is why ordinary instruments cannot detect them. Scientists need extremely sensitive detectors that can measure tiny changes in distance. They also need to remove noise from traffic, vibrations, temperature changes, and many other disturbances. Gravitational waves are real, but their signals are incredibly faint. LIGO is one of the most famous gravitational wave detectors. Its name stands for Laser Interferometer Gravitational Wave Observatory. LIGO uses long arms with laser beams traveling along them. When a gravitational wave passes through Earth, it can stretch one arm slightly while squeezing the other. The change is extremely tiny. But by comparing laser light traveling along the two arms, LIGO can detect the difference. This allows scientists to measure waves from black hole mergers and neutron star collisions far across the universe. LIGO detects tiny changes in space itself. Gravitational waves teach us about events that may be difficult or impossible to study using light alone. They help scientists study black holes directly. They reveal how massive objects spiral together and merge. They allow us to test Einstein's general relativity in extreme conditions. They also help us learn about neutron stars, dense matter, and the behavior of gravity under powerful conditions. Gravitational waves are not blocked by dust, gas, or ordinary matter in the same way light can be. So they carry information from some of the most violent events in the universe. Gravitational waves give us a new way to observe the universe. For most of history, astronomy depended mainly on light. Scientists studied visible light, radio waves, X-rays, gamma rays, and other forms of electromagnetic radiation. Gravitational waves added something new. They gave astronomers a new messenger from the universe. Instead of only seeing cosmic events, we can also detect the ripples they send through spacetime. This is sometimes called gravitational wave astronomy. It allows us to study black holes, neutron stars, and extreme gravity in a new way. Gravitational waves opened a new window on the universe. Let us now gather the key idea. In Einstein's general relativity, gravity is connected to the shape of spacetime. Mass and energy can curve spacetime. When massive objects move violently, they can create ripples in that spacetime. These ripples travel outward across the universe as gravitational waves. They are extremely faint by the time they reach Earth, but sensitive detectors such as LIGO can measure them. They help us study black holes, neutron stars, and extreme gravity. The key takeaway is simple: spacetime can carry waves. Thank you for learning with Prep for Uni Online. If you want to understand relativity more deeply, continue with our lessons on spacetime, general relativity, black holes, the speed of light, time dilation, and modern physics. Prep for Uni Online provides free university preparation resources for students exploring physics, engineering, science, technology, mathematics, humanities, business, health, and the arts.